Hello everyone, my name is Ashley Goodnight and this is my Reading Week 7 video. This week we explored another fundamental concept of physics, the energy principle. Energy comes in many different forms and can often be transformed from one to another. We can apply the energy principle to connect seemingly unrelated processes by examining the change or transfer in energy of a system and its surroundings. One type of energy we explored more in depth this week was kinetic energy. We can solve for the kinetic energy in an object with the equation K equals half m times v squared. Applying our understanding of the momentum principle, we can rewrite this as K equals half times the absolute value of momentum squared divided by the mass. It's also good to know that this equation operates under the assumption that the velocity is significantly slower than the speed of light. We also explored the concept of work, which can cause a change in the kinetic energy of a system. Work occurs when forces act to transfer energy into or out of a system. The magnitude of work depends on the magnitude of the force and how far the object moves. We can mathematically calculate the quantity for work through the equation W equals magnitude of F times the displacement times cosine theta. Sometimes the work won't happen in the same direction as the kinetic energy. We will also need to know how to apply the energy principle in cases where the work occurs at an angle in the opposite direction of kinetic energy and perpendicular to the kinetic energy. Watching this week's lecture videos, I reviewed some ideas I had learned before. For example, I previously knew that energy was a scalar measured in the quantity of mass times length squared divided by time squared, which in SI units is kilograms meters squared over seconds squared, called a joule. However, I did not know that, in general, we can't use the energy principle to solve for vector quantities. What I found to be the most difficult and confusing this week was the lecture of work by non-constant forces. The equation we used for work earlier only applies when the magnitude of work or displacement does not change. In order to solve cases where this is not true, we divide the path into smaller displacements. By small, we mean choosing a displacement size such that the force under consideration is relatively constant in both direction and magnitude during the displacement. We can also keep shrinking our displacement, which results in the following integral expression for work. In order to improve my understanding, I watched some videos from AK Lectures under their section for classical physics, which really helped and provided great examples. This week's videos apply directly to my major of electrical engineering. Georgia Tech allows EE majors to pursue the thread of electric energy systems, a branch of electrical engineering that explores power systems, power electronics, and electrical machines. As we learned this week, we can transform types of energy into one another. This EE thread explores different methods and approaches to transforming energy into electrical energy. With that, I am concluding my presentation. Thank you everyone for listening. See you all next week.